Imagine a crisp fall evening, the sky a canvas of amber and violet. Suddenly, thousands of starlings appear, performing a breathtaking aerial ballet. This ballet is called a murmuration. It's a stunning natural phenomena that holds the secret to the very essence of life. I am a physicist, and I see something very profound in the flight of these starlings. I see fundamental principles that govern not just these birds, but all of life, from the tiniest of cells to the vastest ecosystems. So, where do we go from here? Let me take you on a journey to discover the physics of non-equilibrium systems, like these starlings, that can account for the phenomena of life. To understand the world around us, we need to grasp two fundamental concepts, equilibrium and non-equilibrium. Let's start with the concept of equilibrium, a state of balance and stability. To illustrate this, let's consider a simple bar magnet. If we could zoom in, we would see that this bar magnet is made up of countless tiny domains, each like a compass needle. In an ordinary piece of iron, these tiny compasses point in random directions. But when we apply an external magnetic field, something remarkable happens. These domains begin to align. This alignment process is an example of what we call symmetry breaking in physics. Initially, there is no preferred direction for the domains. This is a symmetry. But when we apply an external magnetic field, this symmetry breaks. The system chooses a specific direction by aligning the domains. And once aligned, these domains reach a state of equilibrium, stable, predictable, unchanging. If we were to film these domains and play the movie backward, it would almost look identical to the forward version. This is a hallmark of an equilibrium state. Time loses its direction. But this state of equilibrium is not actually where life thrives. In fact, it is the antithesis of life. Life in all its messy, complex, beautiful glory exists far from equilibrium. Now, with this understanding of equilibrium, let's shift our focus to where life truly thrives, far from equilibrium. And let's return to our starlings, a much more complex and dynamic example. You can think of each bird in this aerial ballet as a flying, living compass needle. Just as the alignment of our magnetic domains led to the emergence of a macroscopic magnetic field, these birds align their velocities with their neighbors. But here's a crucial difference. This alignment is ever-changing, responding moment by moment to the movement of neighboring birds. The result is a mesmerizing display of collective behavior that seems to defy explanation. Some people will see a thrashing serpent, some a billowing cloud, or even a pulsing heart in their formation. The flock moves as one, yet it is composed of thousands of individual decision makers. It's a dynamic living system that never settles into the quiet equilibrium of our bar magnet. Instead, it remains in constant motion, perpetually consuming energy to maintain its intricate dance. This perpetual motion, this ceaseless consumption of energy is what we mean by non-equilibrium. And here is where it truly gets fascinating. It is in this state of equilibrium that we find the seeds of life's beauty and complexity. Now, with this understanding of non-equilibrium, let's return to the idea of symmetry breaking. In non-equilibrium systems, like our starling flock, symmetry breaking is not a one-time event leading into a stable state. Instead, it's an ongoing process driven by the constant flow of energy and matter. We see a cascade of symmetry breaking events. Each break in symmetry creates new possibilities, new patterns, new structures. It's like a never-ending game of dominoes where each fallen piece triggers new and unexpected arrangements. This continuous symmetry breaking in non-equilibrium systems is what allows for the incredible diversity and adaptability of life. It's why living systems can respond to their environment, evolve, and create increasingly complex structures. Let's combine these ideas, non-equilibrium and symmetry breaking, and revisit our starling murmuration. The starling murmuration is a perfect example of emergence in a non-equilibrium system. Just as the alignment of the microscopic domains in our bar magnet led to the emergence of a macroscopic magnetic field, the coordination among individual starlings lead to the emergence of the flock's complex and fluid-like behavior. But here's the crucial difference. In the magnet, emergence leads to a stable equilibrium state. In the flock, emergence is dynamic, ongoing. The behavior of the flock continuously emerges from the interactions of individual birds, yet it also guides those same individuals, creating a feedback loop that maintains this system far from equilibrium. This dynamic emergence is a feature of living systems. And it is the same principle that applies to us all. It what allows for a collection of cells to become a thinking, feeling human being, or a group of humans to form complex societies. In each case, the behavior of the whole emerges from, yet it also guides the behavior of its parts. Okay, we have seen non-equilibrium on the grand scale of murmuration. But this state isn't just confined to the macroscopic. In fact, the same principles that we observe in our murmuration are universal, manifesting across all scales of life. So let's zoom in from our murmuration to something much smaller, yet no less wondrous, a single living cell. Within this microscopic world, a drama unfolds that mirrors the same dance that we see in the sky above. In my lab, using advanced microscopes, we can watch proteins, the building blocks of life, organize into waves and spirals of activity that ripple across the surface of a dividing cell. Just as each starling responds to its neighbors to create the sweeping patterns of murmuration, these proteins interact with their molecular neighbors to create patterns that guide the development of life itself. What's truly remarkable is that we can use the same principles of non-equilibrium physics to describe these intricate biological processes. For example, we have discovered that these protein spirals behave like charged particles, with the core of each spiral corresponding to either a positive or negative charge depending on their rotation. And just like electric charges organize electric fields, these focal points of protein activity orchestrate the developmental processes across an entire oocyte. These patterns, they never cease to amaze me. As we watch these protein patterns dance across the surface of a dividing cell, we witness something even more fundamental, another symmetry that life breaks, and that is the symmetry of time itself. Remember our bar magnet? In its equilibrium state, time loses its direction. We could play the movie of the magnet forward and backward, and it would look almost identical. But in the non-equilibrium world of living systems, time is an arrow. It has a clear, irreversible direction. Think of our murmuration. You can easily imagine the video of murmuration played in reverse, but it would immediately look wrong, unnatural. Every wing beat of a starling, every cell division in a developing embryo, and every heartbeat in your chest is a step forward in time that cannot be undone. Let me tell you the most remarkable thing. We can show that this arrow of time is mathematically related to the flow of energy in living systems. In other words, direction of time arises from energy dissipation or arises from how far from equilibrium your system is. We can quantify this using a thermodynamic concept termed entropy. Entropy, simply put, is a measure of disorder. In living systems which continuously exchange energy and matter with the environment, higher energy flows means higher entropy production and more irreversible processes. And in fact, my group's experiments with these protein patterns have confirmed this. Now, this irreversibility is what shapes how we perceive time. And what's truly remarkable is that living systems can create order and complexity while adding to the universe's overall increase in entropy. Okay, we have seen these fundamental principles of non-equilibrium from cells to starlings. You might be wondering, so what? How does this change our view of the world around us? When we embrace this dynamic view of life, we start asking new questions and exploring new possibilities. For example, can we use these fundamental principles of non-equilibrium physics to design new materials that are smarter and more adaptable? Could studying energy flows in ecosystems help us discover more sustainable ways to produce and use energy? And if life is truly a phenomenon of non-equilibrium physics, should we look for the origins of life in places where fluxes and energy flows create the potential for complexity? And by thinking this way, we open ourselves to discovering new forms of life or lifelike processes that we haven't even imagined. And you know what's the most amazing part? We don't have to look far to see these fundamental processes in action. Our own planet is full of diversity that arises from these fundamental processes. Take a coral reef, for example. It's a delicate balance where countless species find their way within the flow of energy and matter. Or think about human brain, where billions of neurons fire in coordinated patterns to create what we call consciousness. Even our societies, with their complex economic and social structures, could be understood through the lens of non-equilibrium physics. As our journey comes to an end, let's return once more to our starlings, seen through new eyes. As the last light fades, they bring their ballet to the final curtain, settling gracefully into their roosts. Through them, we see how energy drives matter to self-organize, how breaking symmetries create diversity, and how time's arrow arises from the processes that drive life. I will never forget that moment in my lab, watching through the microscope as the protein patterns ripple across the surface of the dividing cell with energy flowing and conducting this ballet through time. That moment fundamentally shifted my perspective. I realized that life isn't about reaching equilibrium. It's about maintaining this dance far from it. And it is in this constant flux, this journey of becoming, that the true wonder of existence lies. A dance we're all part of, every moment. Thank you.